So it's getting ready to be on. We're still waiting for some people to show up. We have right now 13 out of 21, so many people are still watching. Did someone just take the picture there? Hey, are you there, message? Like your screen shows like there is. Oh, okay.
What?
Yeah, your screen was showing like it was frozen. So, hello, Anna. Now we together. Okay, I'm here. I'm here. We got Michael. We got John, Mr. Cooper. Yeah, Trevor. I see you, man. Okay, I see James, Dakota. Welcome, us, sir. Yeah, Devin. We are already in class. We are already live. So don't do anything funny, because you do anything funny, it's gonna record it. William.
But if we do something funny, it's going to be on YouTube.
Yeah, that's what I'm saying. So let's avoid to do anything, you know. All right. And so I am stopping the music because no matter how many people are still out there, we must start the class. We're already 3 minutes into class time and we cannot continue waiting. So we are about to start the lecture. Here we go. So that's differential equations, and we have lecture 8, and that is going to be the Wronskian and linear dependence. That's supposed to be 4.1 of your book. All right, and now away from the music, we are back to differential equations, and everybody should be happy at this point that we are getting into the most important thing in this class, starting chapter 4, where we will be solving equations of order higher than 1. Everything we have done so far was first order differential equations. This is a completely new topic that will have nothing to do with the previous topics. And it starts by Wronskian and linear dependence. And I say this is section 4.1 of your book. So 1, got this definition. So the Wronskian, I got someone showing up. All right, let us put them in. Of F1 up to Fn is defined.
I have a question. Could you change the color?
You are
It's like hard to see. Okay, well that's better. You don't have to change the color. Well,
let me see. I know what I'm gonna do to make it better. In a second. First of all, get this, and then the thing is that the light reflects from the window, so it changes the
a whole lot better.
Yeah, so it's the reflection of the light from the window that gets on the screen. So the Wronskian of f1 up to fn is defined as w f1 fn. That's a function. Let's say I'm putting it here. It's equal. And on the first row, it's a determinant. On the first row, we put the functions that we are talking about, f1, f2, all the way to fn. Then on the second row, we put the derivatives of those functions. Prime, prime, 1, 2, prime. So if we have only two functions, then we stop here because we got 2 rows and 2 columns. If we have 3 functions, then we add another row, and what is on that row is the derivative of the previous row. So it's going to be second derivative all the way to n. And if that is 3 functions, then I stop here because I just need 3 by 3 matrix. And I will continue so until I hit to the f n minus 1, which is take n minus 1 derivatives. f2, take n minus 1 derivatives, and get to the last function, and you take n minus 1 derivatives. So this is an n by n determinant. So it could be 2 by 2, could be 3 by 3, could be 4 by 4, could be 5 by 5, and so on. That's when n is 2, that's when n is 3, that's when n is 4, that's when n is 5. So the number of rows that you're writing is equal to the number of functions that you have in there. And you start by putting the functions on the first row. And then go to the second row, put their derivatives. If you need a third row, you put the derivatives of the second row. If you need another row, you continue, and so on. So, examples. Let's say w of x squared. How many functions are in here? 2. So I need 2 rows and 2 columns. So first row, I put the functions x squared. Second row, I put their derivatives. Derivative of x is 1. Derivative of x squared is 2x. That's it. And I compute this. The determinant, how is it computed in algebra? They tell you you multiply the 2 things that are on the diagonal, you multiply the other diagonal, and then you subtract. So that is 2x times x minus 1 times x squared. Can you look, make sure you get what I'm talking about? So you take this times that minus this times that. That's how you do. And now you can compute that. That's 2x squared minus x squared. So that is x squared. So w of x squared is x squared. That's how you compute the Wronskian of 2 functions. Now check something here. Let's say we do w of x squared and x. If I switch the 2 functions in the determinant, what's going to happen? That means put x squared first, then put x. Derivative of x squared is 2x. Derivative of x is 1. And this is equal to x squared times 1, that is x squared, minus 2x times x squared. So x squared minus 2x times x. So that gives you negative x squared. And right here, I'm just going to put that one up here. So the Wronskian of x squared x is negative x squared. And this gives you a general rule, actually, property. The Wronskian of f1, f2 is the opposite of the Wronskian of f2, f1. So if you flip the functions in the Wronskian, then the value gets just multiplied by -1. Are we good till now?
Yes.
So we do some algebra here, right? And you can see you got to be able to find derivatives, because if you don't get the right derivatives, no way you're going to get a Wronskian correct. Now, example 2, if it was a 3 by 3, let's say, what's the Wronskian of x squared, and say 1. Was that 3 functions? How would I find the Wronskian of these 3? Now, I would do this. Put the functions on the first row, x squared, 1. Take their derivatives and put on the second. Derivative of x is 1. Derivative of x squared is 2x. Derivative of 1 is 0. Oh, it's three columns, so you need a third row, right? So derivative of 1 is 0. Derivative of 2x is 2. Derivative of 0 is 0. So that's what the Wronskian is. And now you need to compute this determinant. Now there are some rules. For those who took algebra, it's kind of easy to understand here. Like, you use the minors to compute when you have more than two rows and 2 columns. And you go and you pick the column or the row where you have the most zeros. So I could use either this row or that column because I have the most zeros on that. So I'm going to pick this column to compute it. Why is it important to have the zeros? Because technically what you do when you're using the minors is that you take first -1 raised to the power of the sum of the row and the column. The row is first row, column is third, 3 plus 1 is 4, so -1 to the power of 4. Take the number that is at the intersection of the column and the row, that's 1, so you multiply by it. Then you multiply by the determinant that we call the minor, which is what is left when you remove this column and this row and this column from the matrix. If I remove this row and this column, I'm left with this one. That's what you have here. 1, 0, 2x, 2.
Okay, I have a question.
Yes, sir.
Okay, so I'm in a class and we're on a similar topic as this. And is it okay if we use like the checkerboard method?
You could do anything you want as long as you know all the details of it.
Because I don't understand. How did you get that 4 again? Could you explain that?
It's the sum of the powers of the rows and the sum of the row and column. So this is row 1. This is column 3. So you say 1 plus 3 is 4. So you take -1 to the power of 4. And then you take the number that is at the intersection of that row and that column. You put it right here. And then you multiply by the minor, which is obtained when you remove that row and that column from this matrix. That is 1, 2x, 0, 2. That's it.
All right.
And you keep that procedure for all of them, and it works.
Okay, and where did you get the negative one from?
That's the formula. The formula starts by
Okay.
negative 1.
Always negative one.
Yeah, it starts by negative 1 to the power of I plus j, where I is the column, j is the row. And then the number here is the intersection of the row and column. And then this is what is left when you remove the row and the column. Does that make sense? It might be hard to memorize, but I mean, that's the formula that we use in algebra for determinants when we start. And I know some of you don't take that before this course. That's why I'm taking the time to explain here. Okay. Some of you might have other ways to do that, I mean, maybe somebody else try to explain that to them. You can use it as well. I'm not forcing you to use this one, but I can guarantee that when you use this 1, 2 times, it works, you know. So again, I restart. You start by negative 1 raised to the power, and the power is row plus column. First row, third column, 1 plus 3, 4. And then multiply by the number that is at the intersection of the row and the column. Then multiply by what is left when you remove the row and the column from the matrix. That's the first one. Now you will understand why it is good to take the row or column with the most zeros, because when you do plus, then negative 1 to the power. Now let me say I'm doing that with respect to the column. So I'm moving now from the first row to the second row, keeping that column. So I will have second row, third column. So that is 2 plus 3, 5, right? So that's negative 1 to the 5th. And now I multiply it by the number that is at the intersection of those columns and row. What is it in this case?
0.
0. That's why we love the columns with zeros, because when you put a 0 here, it really doesn't matter what else is coming because it's going to be 0, right? Is that clear? And so that's why the last one, and we just do that last one to make sure you see the power that is going to be there. We still keep that column and we go to the third row. Third row, third column, 3 plus 3, 6, right? But again, intersection of that column and row is 0. So you don't need to know what else is coming. So when you understand this method, you know when you see this matrix that you have only one thing to compute because the rest is going to be 0. And that really saves you a lot of time, right? So from the get-go, I knew I don't have to put this down because it's going to be 0, because I have these zeros here. And so this is going to be equal, negative 1 to the power of 4 is 1 times 1, it's 1. And then here I get 1 times 2 minus 0. So the whole thing is 2. And that's 0, 0. So the Wronskian of x squared 1 is 2. Is everybody good with this? Any questions? Now you might ask yourself, we are doing differential equation and all of a sudden we start talking Wronskian and then say taking derivatives, computing these things and talking about algebra course. What does it have to do with differential equations, right? And the answer is, when you have equations of order higher than 1, this thing is very important. It comes pretty handy in many problems, helping to find the solution, helping to show that the solution that you have is the only one and that there is no other one. All right. Let me use that fact, what I'm explaining here. So, 2 linear independence of functions here we will say in this course that f1 to fn are linearly independent even only if the Wronskian of f1 all the way to fn is not equal to the function 0. And that says they are linearly independent. F1 up to Fn are linearly dependent if W F1 Fn is equal to 0 for all x. That means that when you compute the Wronskian, the value you see is 0, the function 0 for all values of x. So you're not solving for x to say that for this value of x, it is equal to 0. You just compute and it is right there, 0. No matter what is x. As example, the first example we computed was w of x, x squared. And we found out that it was x squared, right? And x squared is not 0. It's not the 0 function. So x squared are linearly independent. And I refuse to get into some of the considerations that you do here about showing why this is equivalent to these functions being linearly independent, because it's really not adding anything to this course. That's algebra. Let them worry about that in the algebra course. We just use here what is going to help us in solving our problems. So, but actually, I think most of you do know that the functions x and x squared are linearly independent, right? Because these are two polynomials of different degrees. And you know that's why when you're writing a polynomial of degree 2, you have a plus bx plus cx squared, because they are independent. So we just show that they are. And so we also computed w of x squared and 1, right? And we figured that that was equal to 2. Is that so? Is that what we got? On the previous page. It's w of x squared 1 is 2. So, and 2 obviously is not 0, right? Unless we live in a world where 2 is equal to 0, this thing is not 0. And if it's not 0, then also the functions 1x squared are linearly independent. Does that make sense? Now let me show you some other crazy functions that you could have. Example 3. Let's say we have, and I ask the question, are these functions linearly independent? And that's f1 equals e to the x, f2 equals e to the negative x, and f3 equals sine hyperbolic of x. And first of all, your first question would be, what is sine hyperbolic of x? What does that mean? Right. And then I'll say, it's fine if you don't know. You don't have to know. So here, sine hyperbolic of x is actually a crazy way of saying e to the x minus e to the negative x over 2. That's what they call sine hyperbolic of x. And now you need to know whether these functions are linearly independent or not. So you put them in W. So what's W of f1, f2, and f3? And so we go. First function, e to the x. Second function, e to the negative x. Third function, e to the x minus e to the negative x over 2. Here we go. So we have our first row. Now we go look for the second row. The second row is the derivatives of the first row. So derivative of e to the x is e to the x. Derivative of e to minus x is negative e to the negative x. And derivative here is going to be e to the x plus e to the minus x over 2. And because we have 3 columns, we also need 3 rows. So we take the derivative of the second row to get the third row. Derivative of e to the x, it's e to the x. Derivative of e to minus x is minus. Minus and minus cancel, so that's e to the minus x. Derivative of this one is e to the x minus e to the minus x over 2, right? That's it. Now we can compute this determinant the way we are used to, but we can also use the knowledge from that algebra course. In that class, you say, if two rows of the same determinant are either identical or one a multiple of another, then the determinant is equal to 0. So this thing is going to be equal to 0. And I put the eyes and a smiling 0 on it. Now we know it's going to be 0. If we know that course, we use that property, we get it. Now, if you don't know that, let me just compute it as if I didn't know that it's going to be equal to 0 using the properties that I gave you on the first example. Why is this thing equal to 0? I say 0 because row 3 equals row 1. That's good enough explanation for that to be 0 in algebra. Now here, let's compute it the way we did the computations for the first example. So we are going to write, and I start also by that last column. So I get -1 raised to the power, starting third column, first row, that's going to be 4 times what is at the intersection of the first row and third column. It's e to the x minus e to the minus x over 2, and then the determinant of e to the x minus e to negative x, e to the x, e to the negative x. That's the first part. then plus minus 1 to the power. Now I go to the second row, still keeping that third column. So that's power 5. Second row, third column, 2 plus 3, 5. The number at the intersection of the two is this one. Look carefully as we are doing. So that's e to the x plus e to the minus x over 2. So e to the x plus e to the minus x over 2, and then you multiply by what is left. When I remove this row and that column, what is left is these first two and these two. So that's e to the x, e to the minus x, e to the x, e to the minus x. And then plus negative 1 to the power. I take the third row and third column, that's power 6 now. Number at the intersection, that's e to the x minus e to the minus x over 2. And then the minor. When I remove this and I remove that, I am left with these two and those two. So that is e to the x, e to the minus x, e to the x minus e to the minus x. That's what you get. That's it. Now we go in here and we start figuring out what this thing is all equal to. So this is equal, negative 1 to the power 4 is 1. Then you got e to the x minus e to the minus x over 2 times. Now e to the x times e to the minus x. Please look carefully. Again, I'm going to explain this right here. E to the x times e to minus x. That's e to the x minus x. That's e to the 0, that's 1. Same here, 1. Same there, 1. So that's times that, that is 2. 1 plus 1, 2. Minus 1 to the power 5 is minus 1. And then you got e to the x plus e to the minus x over 2 times. And here, e to the x times e to the minus x, it's that same thing. It's 1 minus 1, 0. So right here, it's times 0. Now, negative 1 to the power 6 is plus 1. E to the x minus e to negative x over 2. And again, e to the x times e to the minus x, that's the same 1. But now it's with a minus, so it's minus 1, so it's times negative 2. Now this piece is 0. This thing is same as that. It is times 2. Here it is times minus 2. Thus the whole thing is our smiling 0. And that means that e to the x, e to minus x, and sine hyperbolic of x are linearly dependent. You can see that here, this thing is equal to 0 no matter what x is. So we are not choosing a value of x to plug in to say that it is 0. It's 0 no matter what x is. That's the point. So linear independence is about the whole thing being 0, no matter what you plug in it. So now please you do this one. F1 is cosine of x. F2 is sine of x. And F3, let's say is 1. You answered the same question. Are the three functions linearly dependent or independent?
I have a question.
Yes, sir.
Is the sine square x plus cosine square x, isn't that one of the like identities for like it equals one?
Yeah, that's it.
So this problem is linearly independent.
Well, that it would depend on the steps that you used, right? It should be linearly independent if that's what you come up with. Did you compute the whole thing?
Yes, sir.
All right, that's I sense your answer is correct. So you have cosine x, sine x, 1. Derivative of sine is negative, of cosine is negative sine x, and derivative is cosine x. Derivative of 1 is 0. Derivative here is going to be negative cosine x. Then you're going to be negative sine x. And here is going to be 0. And so just as the first example we had, because we got two zeros here, the only thing that we are interested in is the first one. So it's going to be 1 times negative sine x, cosine x, negative cosine x, negative sine x. That's what remains when you remove the first row and the third column. And when you do that, negative, negative, that's sine square x plus cosine square x, and that's 1. And 1 is not 0, so We got cosine x, sine x, 1 linearly independent. Any questions? So that's basically what the thing is, and that's how it works. Now, the third thing here is what we call the fundamental set of solutions. Fundamental set of solutions of the equation an nth derivative an minus 1 n minus first derivative to a2 second a1 first derivative a0 y equals 0. So that's the actually the object that we will be working with, a linear equation of order n in general, but then we'll reduce it to order 2 and then down to fixed coefficients to show how you solve them in those particular cases. So we have an equation of this type, and what we call a fundamental set of solutions of this equation is a set of functions y1 up to yn, a set of n, because the order of the equation is n, you need n of them, a set of n functions such that one each of them is a solution of the equation, and 2 are linearly independent. Linearly independent meaning w of y1, yn is not equal to the function 0. And that's the link between that topic and the differential equations that we are solving.
What's the subscript on the first in the brackets right there? The y in something one?
We're here.
Yes. No, one below that. Like yeah, that one right there.
To y1 up to yn. The functions y1 up to yn, a set of n functions such that each of them is a solution of the equation that is given, and then they form a linearly independent set, which means the Wronskian is not 0. Such a set is called a fundamental set of solutions of the problem. Why is it called a fundamental set of solutions? Because using some properties that we learn in algebra, we can show that any other solution of this equation can be written as a linear combination of these solutions. So any solution, let me call this equation star, can be written as y of x equals c1 y1 plus c2 y2 all the way down to cn yn when y1 yn is a fundamental set of solutions. Now notice that it always goes up to n when you have an equation of order n. So I have an equation of order 2, I need 2 functions. If I have an equation of order 3, then I need 3 functions. Order 4, 4 functions. Order 5, 5 functions. So there are as many functions as the order of the equation in the fundamental set of solutions. Example 1. Let's say we have second derivative minus the function equals 0. And I say, show that e to the x, e to the minus x is a fundamental set of solutions. And what you're going to do is first realize that 1, the equation is of order 2, and we have 2 functions. That's very important, because if it's not as many equations, as many functions as the order of the equation, then it's useless to continue. It can't be a fundamental set of solutions. So the equation is of order 2, and we have 2 functions. That's the beginning. 2 is each of them a solution. So take, say y1 equals e to the x, derivative y prime is e to the x, second derivative is e to the x. And then you're gonna plug them into that equation. That's how you check. We did this before. How do we check that a function is a solution of an equation? You take that function, take derivatives, and then plug into the equation to see if the equation is satisfied. So here I'm gonna take second derivative minus the function equals, second derivative is e to the x minus the function is e to the x. E to the x minus e to the x is 0. So yes, this is a solution. Now you take the second one and you check as well. It's e to the negative x. The derivative is minus e to negative x. The second derivative is minus minus plus e to negative x. And again, you check second derivative minus the function. Second derivative is e to negative x minus the function is e to negative x. And you have e to negative x minus e to negative x, it's 0. So yes, as well, each of them is solution. Now you have the third thing that is left, which is show that the Wronskian is not 0. W of e to the x, e to negative x is e to the x, e to negative x, e to the x derivative negative e to negative x. And this is minus 1 equal negative 2. And negative 2 is not 0. So these are linearly independent. So linearly independent solutions, two of them, therefore, they form a fundamental set of solutions. E to the x, e to the minus x forms a fundamental set of solutions. That's it. Questions? Any questions? Now let me give you an example, another example. The equation is, let's say, second derivative plus twice the derivative minus 3 times the function equals 0. And I'm going to check e to the x and e to the negative 3x. So the question is this a fundamental set of solutions? So you repeat the same things we just did in the other example. Any ideas? Well, anyone ready to present his work?
I can show mine, but I don't know if it's right.
Yeah, I'm sure you get it right. So what's the first step? Okay, you want me to share? Let me just click on it then. Spotlight. Okay, so the first step says you've computed the Wronskian of the two. It's not zero, that's right. And show that each of them is a solution. Plug that in as taking derivatives. Okay, that one is right. And then take derivatives. All right, plug them in, right? Checking correctly that each of them is a solution. And then what's missing? You just need to tell me that it's two functions and the equation of us is of order 2. That's it. Perfect. Great, thanks. So that's how we do. We take derivatives and we show that each of them is a solution. We find the Wronskian. We show the Wronskian is not zero. And we remind that, yeah, it's two functions and the order is 2, and therefore conclusion, that's it. So here it's two functions, an equation of order 2, important. Then check that each of them is a solution. If you take y1 equals e to the x, y1 prime is e to the x, y1 double prime is e to the x, same. So you plug them in, you got e to the x plus 2 e to the x minus 3 e to the x, 0. That's true. So the equation is satisfied. The second function is e to negative 3x. Derivative is negative 3 e to negative 3x. Second derivative is 9 e to negative 3x. So you plug them in. Second derivative 9 e to negative 3x plus 2 times negative 3 minus 6 e to negative 3x minus 3 e to negative 3x equal, that's 9 minus 6 minus 3, 0 as well. And we can say that this 0 is smiling because it is seeing that everything is correct. So that equation checks as well. So each of them, each of the two is a solution. And then the last thing is check for the Wronskian, w of e to the x, e to the negative 3x, that is e to the x, e to negative 3x, e to the x derivative here, derivative minus 3 e to the minus 3x, and you multiply that, that's minus 3 e to the x times e to minus 3x minus e to the x times e to minus 3x. Now e to the x times e to minus 3x is e to the x minus 3x, e to the minus 2x. Minus 3 minus 1, that's minus 4, e to minus 2x. And this is certainly not 0. So linearly independent. Thus, we have two functions that are solution, each of which is solution of a second order differential equation, and they are linearly independent. Therefore, e to the x, e to minus 3x is a fundamental set of solution. That's it. Any questions? It is so calm. Does it mean that everything is okay? That everybody understood this and we can move on? All right. Are we good, James? All right. Maybe he's not here. Okay. Let's see here. About Abel's theorem. Let's say we have an equation of the kind second order plus p of x first derivative plus q of x y equals 0. And this is leading you into the next topic that we will have next week. So let's say W is the Wronskian of any two solutions, y1 and y2, any two solutions of this equation, then W prime plus P of X W equals 0. So the Wronskian of any two solutions of such problem is always a solution of this first order linear differential equation. And if that is the case, we have solved in general already this equation to mean that W is equal to C e to the negative integral of P of X dx. So the Wronskian of any two solutions of this equation can be computed by the formula W equals C times e to the negative integral of P of X. So we can take time to actually prove that this is true, but we don't need it. It's very easy, actually. You just write the formula of the Wronskian that we use, open the parentheses, cross multiply, and then add and multiply here to see that it's equal to 0. So it's really not necessary to spend the class time just on that. So examples of use of this are going to come next time. Let's say we have an equation y double prime minus 2x y plus 3 over x equals 0. You have an equation of this form. Then P of x is that function that is in front of y prime. P of x is negative 2x. And w is equal to c e to negative integral of negative 2x dx, which is c e to the integral of 2x dx, which is c e to the x squared. So that's what the Wronskian of any two solutions is going to be. So no matter what you are taking as solutions of that equation, the Wronskian of the two is going to be a constant times e to the x squared. Am I making sense here? All right. If we have such an equation, 3x y double prime minus 4 y prime plus 5x squared y equals 0, and then in this problem, you need to make sure you have the problem written in this form first before you apply that rule. So you need to make sure the coefficient of the second derivative is 1. So this is first going to be transformed to y double prime minus minus 4 over 3x plus 5x over 3 equals 0. This is y prime, this is y. And only in this form can we identify p of x. So that's the p of x. And so w is going to be c e to negative integral of p of x dx, which is c e to negative integral of negative 4 over 3x dx, which is c e to the 4/3 ln of x, which is c e to the ln of x to the power 4/3 equals cx to the power 4/3. So that's what the Wronskian will be equal to in this case. And you remember that you always, when you have a coefficient here, you put it inside as power. That's why 4/3 goes inside as power of x. And e to the natural log turns into x to the power 4/3 in this case. That's it. So for now, we can say we have learned how to use the Wronskian first here to show that we have a fundamental set of solutions. We have seen how we can compute the Wronskian of an equation of second order without knowing what the functions are. We can always compute that Wronskian and see that it's c times e to the negative integral of p of x dx. This will be very important next time because we will use it to do what we call reduction of order of an equation. Take an equation of second order, knock it down to an equation of the first order, solve it using this property. That will be it from me today. If you have any questions, you ask them. If you don't have a question, then I would say till next time. Good.
I have a question.
Go ahead.
I don't know if we're going to learn this at some point in the future, but how do you derive those functions in the first place? Like the functions that you gave us to test, how do you?
Right here, we just give them. And in such a question, you will just have them and you will have to show. that they form a fundamental set of solutions. Now, for specific types of equations that are coming, I will show you how to find the functions in those cases. And the question there will be different. The question will be solve the equation.
All right. Thank you.
Welcome, sir. Anything else?
Have a good weekend.
Oh, it's same to you.
Have a great day.
See you and
Thank you.
bye.